Hello everyone, welcome to the second part on the discussion of slope deflection method. So if you missed to watch the first part of this discussion, I have presented the link of the first part in the description below. So by the way, to those who are new, I am Engineer J, a civil engineer and an engineering professor. So we have the slope deflection method and we are going to solve more problems of our analysis on indeterminate structure. Okay, but this part 2 is special because we will be introducing here a new slope deflection equation. So in our previous discussion, I have introduced the slope deflection method equation in which we have this m in f is equal to the fixed end moment plus 2ei over L times 2 theta n plus theta f minus 3r. However, there are cases that the slope deflection equation could give you a much longer time or a much longer procedure of analysis. So there is cases that we can use this modified slope deflection equation, especially if you have a ruler or a hinge exterior support in which the moment on the farthest left or farthest right is equal to 0. Though you can still use the general slope deflection equation, but I am sure that it would take you a longer procedure because it could involve a number of or a much larger number of unknown variables, and that of course would require a much number of general equation so that you can compute for the member end moments. Okay, so how and when to use this modified slope deflection equation? So like for instance, if you have a continuous beam in which the farthest left is h and the interior ruler is r, okay, we know that our moment here, let's say this is our mhr, this is equal to 0, right? But we have moment MRH. Now to compute for the member end moments MRH, you have to use this modified slope deflection equation. So this is just an option just to make your procedure or your solution shorter. You can still use the previously mentioned slope deflection equation, but this can be applied especially if you want to expedite the process. Okay, so we have MRH is equal to 3ei over L times theta r. Okay, this is the angle at point R minus r. R is the chord rotation in which we have the formula. We have the delta over L. Okay, especially if you have settlement, so you have to use this r here. Plus the fixed end moment RH. So again, fixed end moment can be used the formula that I have presented. So again, just to give you a quick overview, so these are the formula for fixed end moment. So it depends on the load of the beam. So all you need to do is create a restrained beam in which, like this one, so we have PL over 8. If we have our concentrated load on the midspan, so you just need to familiarize this fixed end moment. But the most commonly used one is when we have a uniformly distributed load all throughout our beam, in which the fixed end moment is WL squared over 12 on both supports. Okay, so you have to familiarize this fixed end moments formula minus the fixed end moment on the HR side over 2. Okay, so if you want to know which side is FEMR8, so you just need to create a restrained beam. So you have to create a restrained beam here. On this side is the fixed end moment of HR, and on this side is the fixed end moment of RH. So this modified slope deflection equation could help you in solving or in making your solution much shorter. Again, this can only be applied if our MHR is 0. Okay, so you just use MRH as using this modified slope deflection equation. Okay, so let's try to apply this new equation that we used here, that we have just discussed by solving problem number 2. So we have here, determine the member end moments and reactions of the 3-span continuous beam shown due to the uniformly distributed load and due to the support settlement of 15 mm at B, 36 mm at C, and 18 mm at D. So we are asked to use the slope deflection method. Now take note, we have support settlements here. This could give us the value of our chord rotation, R. Okay? So obviously, this is an example of indeterminate structure because we have a 4 supports with 5 external reactions. Now we have hinge, which has 2 reactions, and 3 ruler support, which has only 1 reaction each. So we are asked to compute for reaction A. So we have reaction A, this is RAY, reaction B, reaction C, and lastly we have reaction D. And of course, we have horizontal reaction at A, but this is equal to 0 because we do not have horizontal exterior or external loads on the beam. Okay? But due to the support settlement, we have this exaggerated deflection of our beam in which B would settle 15 millimeters. This one. C would have a settlement of 36 millimeter, and D would have 18 millimeter settlement. So again, since we have settlement, our chord would have a rotation. Okay, so we have now to compute for the member end moments by, of course, dividing these structures into segments at point of discontinuity. Now we know that we can divide it into 3 members. We have AB, BC, and CD. So we will begin with member AB. So the free body diagram of AB would show us, of course, the reaction A and the left side reaction of B, or RBL. It has, of course, a length of 5 meters. So at point A, we have MAB. We assume that the rotation is counterclockwise, and on the side of B, we have MBA, and we assume that the rotation is clockwise, and that means this rotation here constitutes negative reaction or negative value. Okay? But again, we know that our MAB is equal to 0. Again, since we have hinge or external hinge at that point, and again, when we have hinge support, again, there is no moment at that point. Okay? So, wala tayong moment. So in that case, since our MAB is equal to 0, then we can say that our MBA can be computed using the modified slope deflection equation, in which we have, again, 3 EI over L times, we have theta B minus the chord rotation plus the fixed end moment of BA minus the fixed end moment, we have AB over 2. Okay? So we have to substitute the available values here. So we have MBA is equal to 3 EI. Of course, our length is 5. We have theta B minus R. Here is the chord rotation. We have the formula, the change in support settlement over the length of the beam. So as we all know that A and B would have a chord rotation because we have a support settlement at point B, and the deflection is 15 millimeter vertical movement or vertical settlement. So as what you can see, our chord here, our beam rotates in clockwise direction with respect to A, and of course clockwise direction with respect to B. So this is our R, AB, and this is our RBA. Now, so to compute for R, we just need to determine the change in support settlement over the length of that member. So we have, now again, we know that the settlement is 15 millimeters over the length of the cord, or the length of the member, we have 5 meters, or that is 5,000 millimeters. Okay, so we have R here, which is equal to 0.003, and we can cancel out millimeter here. That would give us a unit of radian, because we are dealing here rotation of cord. So therefore, we are computing here the slope. Okay, now what would be the sign of the rotation here? Now take note, the rotations, or the slope, rotates in clockwise direction, right? So therefore, since this one is clockwise, that means we have negative sign. If you have counterclockwise rotation, that is, we have a positive sign convention. Okay, so the same as with a moment, okay, that if we have a counterclockwise moment, that means that moment is positive in value, and if we have a clockwise moment, that means it has a negative value. But in this case, we have a clockwise rotation of cord, therefore this one is negative. Okay, so we have here negative 0.003 plus the fixed end moment. Again, to compute for the fixed end moment, you just create a restrained beam with 2 fixed support at both ends. So we have the uniformly distributed load, which is 32 kilonewton per meter. Okay, and then we have, of course, the length 5 meters here. So this is our fixed end moment of AB, and this one is fixed end moment BA. So our sign convention is the moment on the left support rotates counterclockwise, while the moment on the right support rotates clockwise. So again, if we have uniformly distributed all throughout the beam, so as what you remember, okay, on the figures that I have presented, so I have already presented to you the formula for fixed end moment. So in the case that we have a uniformly distributed load that acts all throughout the beam, that means our fixed end moment here is WL squared over 12 on the left side, that's positive, and we have negative WL squared over 12 on the right side. Okay, again, this one is negative because we have a clockwise rotation. So that means we have WL squared over 12, we have 32 times 5 squared over 12. This would give us negative 66.667. So the fixed end moment on the left is positive 66.667 kilonewton meter. So we have FMBA, which is negative 66.667, minus FMAB is 66.667 over 2. Since they are both negative, then you add. So we can simplify it further by multiplying these values here. We have 3 EI theta B over 5, then plus 0.0018 EI, okay, minus, so if you sum this up, we would have negative 100 kilonewton meter. Okay, so this is now our equation for member and moments of BA. So this is now our equation number 1, and we will go back to this equation later on if we have already done with the generation of all the member and moments equation. And then let's proceed to member BC. So on the free body diagram, we have 32 kilonewton per meter uniformly distributed load that acts throughout B to C. So we have the reaction here, which is the right side reaction of B, so RBR. And on this point here, we have the left side reaction of C, we have RCL, and we have 5 meter length. So we have this moment here, this is MBC, and we have moment here, we have MCB. So we need to create a moment equation for MBC and MCB using the slope deflection equation. But this time, since neither of these two moment here is equal to 0, correct? So that means we will use the basic slope deflection equation. Okay, the m and f is equal to, we have 2 ei over L times 2 theta n plus theta f minus 3r plus the fixed end moment nf. Okay, so we will be using this one because again, the modified slope deflection can't be used in this case because neither of these two moment is equal to 0. So we have MBC is equal to, okay, let's begin with the fixed end moment. Now, fixed end moment, this is the same as with the first free body diagram, in which MBC here is 66.667. This is the fixed end moment BC, and the fixed end moment CB is equal to negative 66.667. Again, they have equal value with member AB because they have the same load. Okay, they have 32 kilonewton per meter load, which is the same as with the free body diagram, or the same as with the member AB. Okay, and also they have the same length, 5 meters. We will no longer compute for fixed end moment because we have already done this from the previous free body diagram. Again, since they have member AB and member BC has the same uniformly distributed load and the same length, that means they should have the same fixed end moments. So we have here fixed end moment for BC is 66.667 plus we have 2 EI over the L, the length is 5 times 2 theta B plus theta C minus 3R. Okay, now our R here, we have the rotation of B to C. Okay, so this has a rotation of clockwise, and the delta, or the change in support settlement, is equal to, we have for theta BC, the change in settlement is equal to 36 minus 15. Correct? So we have R is equal to 36 minus 15 divided by the length, which is the same. We have 5 meter length, so therefore this one is 5,000. Okay, these are all in terms of millimeters. You can cancel out. The remaining would be in terms of radian. So we have the answer here. We have 4.2 times 10 raised to negative 3. Okay? So let's change this R here by, now the unit, the sign is negative because the rotation is in clockwise direction. So that is negative in value. So we have negative 0.0042. Okay, so we simplify it further. We have MBC is equal to 66.667 plus we have 4 over 5 EI theta B plus 2 over 5 EI theta C. Then we have plus 0.00504 EI. Okay, but again, to shorten the number of variables here, we can just unite these variables. We can use theta prime B. This prime here indicates that this variable is a factor of EI and theta B. Okay, so we have MBC is equal to 66.667 plus we have 4 over 5 theta prime B, okay, plus 2 over 5, we have theta prime C, plus 0.00504 EI. So this is our equation number 2. And we have now to proceed to MCB. We have MCB is equal to the fixed end moment. We have negative 66.667, correct? That is the fixed end moment on the right support, or okay, on the right end of the restrained beam, plus we have 2 over 5, again because our L here is still 5, then EI times 2 theta C plus theta B minus 3R. So our R here is the same. Our R is negative 0.0042 because that is the rotation of member CB. So we have MCB is equal to negative 66.667 plus 4 over 5 EI theta C plus 2 over 5 EI theta B, then plus 0.00504 EI. So we have the final equation for member end moments of MCB. We have negative 66.667 plus 4 over 5 EI theta C plus, okay, so again you can unite this EI theta C here as theta prime C plus 2 over 5 theta prime B plus 0.00504 EI. So this is now our equation number 3. So we are now done with member BC. So we'll now proceed to member CD. So on the free body diagram, we would have here the right reaction of C. Okay, that's RCR. And the reaction of D, we have RD. And again, we have moment here, we have a moment CD, and we have here moment DC. Now take note, our moment DC here is equal to 0, correct? Because that is a ruler support at that point. Again, we do not have moment when we have a ruler or hinge support on the farthest right or farthest left. So in this case, we will be using the modified slope deflection equation for MCD. Since MDC is equal to 0, therefore MCD here can be used by the formula 3EI over L times theta C minus R plus the fixed end moment CD minus the fixed end moment DC over 2. Okay? So we have MCD is equal to 3EI. Our L here is the same. We have 5 meters. So we have 5 times theta C minus R. Now take note, going back to this deflection, C and D would have a chord rotation, and the rotation is in counterclockwise direction, just like this one. This is counterclockwise direction. So even if we change the orientation with respect to D, so we have still counterclockwise at that point. Now, again, if that is counterclockwise, that means we have positive value for rotation. To compute for the rotation R, so we have to compute for the change in settlement over the length. So we have 36 minus 18 over L. L here is 5,000. So we have R is equal to, so 18, because we will be, we subtract 18 from 36 because the length here is our delta. Okay, so delta is 36 minus 18. So we have the answer 0.0036, and the sign is positive because again the rotation is counterclockwise. So we have minus R. Our R here is positive 0.0036 plus the fixed end moment CD. Again, we have the same fixed end moment with the previous free body diagram because we have the same load as the others and the same length as the other free body diagram. So therefore, our fixed end moment here, CD, is positive 66.667, and here we have FEM DC is equal to negative 66.667. So we have here 66.667 minus if EMDC is negative 66.667 divided by 2, and we further simplify this equation, MCD is equal to, so we multiply, we distribute 3 over 5 inside the parentheses, then we have 3 over 5 EI theta C minus, we have 0.00216 EI, then plus, if you add these two values, then we have 100. So our final equation is MCD is equal to 3 over 5. We have theta prime C minus 0.00216 EI plus 100. So this is our equation number 4. Okay, so we have now 4 equations. So initially we have 4 equations. We have MBA, MBC, MCB, and MCD. But take note, we have how many unknowns here? We have unknown, we have theta prime B, we have also theta prime C, and we have a moment BA, moment BC, moment CB, and moment CD. So we have 6 unknowns, but we only have 4 equations available. So in this case, we have to add 2 conditions, okay, so that we can minimize, or we can decrease the number of equation. Okay, now this is the advantage if you use the modified slope deflection equation. If you will be using the general slope deflection equation, you would have a theta A here, or theta prime A, which can add to your number of unknowns. So you need to have more number of equations. So that's the advantage of using the modified slope deflection, because theta prime A here was eliminated, and as well as the theta prime D, as what you can see. Okay, so we have to add 2 equations or 2 conditions here, just to satisfy the number of unknown variables. Now, upon looking at this diagram, we can have this joint condition in which, since we know that at point B and at point C, our force there should be in equilibrium. Okay, so therefore, if we have moment BA and moment BC, these 2 moments here should have the same magnitude. So therefore, we have MBA plus MBC. This should give us 0 sum. Okay, and the same as with moment CB, which has also the same value with moment CD. So if you add these 2, we have MCB plus MCD. This would give us 0 as well. So these 2 conditions can help us to decrease the number of unknowns. Okay, so we have these joint conditions, MBA plus MBC, this equals to 0, and MCB plus MCD is equal to 0. So these are the 2 additional conditions that would minimize the number of unknowns. So let's begin with 5. Okay, now for this equation, we have to use the equation number 1 and plus equation number 2. Okay, so we have equation number 1, 3 over 5 theta prime B plus 0.0018 EI minus 100 plus, so again, this is our moment BA, plus the moment BC, we have 66.667 plus 4 over 5 theta prime B plus 2 over 5 theta prime C plus 0.00504 EI. Again, this is our MBC, and this equals to 0. So by further simplifying, we have 3 over 5 theta prime b plus 4 over 5 theta prime b plus 2 over 5 theta prime c, this one. Then we can equate all the constant to the right side of the equation. We have minus 66.667 plus 100 minus 0.0018, this EI minus 0.00504 EI. Okay, so we can add theta prime b here. We can combine. We have 7 over 5 theta prime b plus 2 over 5 theta prime c, and this equals to, now you can add this constant. Now these two can be much simpler by substituting the value of EI. Okay, so again we have the value of EI. E is 200 gigapascal. I is equal to 1705 times 10 raised to the 6 millimeter to the fourth. So by changing all the units, because we are required to come up with kilonewton meter here. Okay? So you can just simply convert manually all the units to meter and kilonewton, or to make it simpler, you just multiply 1705 and 200 gigapascal. That would give you 341,000, and the unit here is, since this one is in kilonewton meter squared. So I will leave the conversion to you. So ikaw na lang yung mag-convert. So in this case, we have to multiply this 341,000 to 0.0018 and 0.00504. So we have 0.0018 times 341,000 and 0.00504 times 341,000, and then this would give us 613.8. The other one is 1718.64, and the unit is in kilonewton meters na. So we add this all constant by using these values. So again, this can be replaced by 613.8, and this one is 1718.64. We have the entire constants equal to, so we have here negative 2299.107. So this now our new equation. Okay, let's say this is our equation number 7. And we have to create another equation by using this equation number 6, in which we have MCB. We have the third equation plus the fourth equation, and this should be equal to 0. So we have again the third equation plus the fourth equation is equal to MCB is equal to negative 66.667 plus 4 over 5 theta prime C plus 2 over 5 theta prime B plus 0.00504 EI. Okay, this is our MCB plus our MCD. We have 3 over 5 theta prime C minus 0.00216 EI plus 100, and this equals to 0. So we can further simplify this. We have 2 over 5 theta prime B plus 4 over 5 theta prime C plus 3 over 5 theta prime C equals to, now let's move all the constants to the right side of the equation. We have positive 66.667 minus 100 minus 0.00504 EI plus 0.00216 EI. Again, this EI here equivalent to 341,000 41,000. Okay, this 2EI. So we can simplify this equation further by summing up all the constants and all like terms. We have 2 over 5 theta prime B plus 7 over 5 theta prime C. This equals to negative 1015.413. So this is now our equation number 8. Now we have now these two equations, 7 and 8. We have unknown theta prime B and theta prime C for both equation. Then we can now apply simultaneous equation. You can use your calculator or you can use the algebraic procedure. But to expedite the process, I would show directly the answer. So we have the value for theta prime B, which is equal to theta prime B equals to negative 1562.547. Again, this is not the value of rotation because again, theta prime B here is a factor of EI and the slope theta B. So if you wish to compute for theta B, then you need to divide this by EI. So we have theta B here is equal to negative 1562.547 over EI. So that is the value of the slope at B. And our theta prime C is equal to negative 278.853. And the unit is in terms of course, kilonewton meter squared. So, this is kilonewton meter squared. So, since we have now the value of theta prime B and theta prime C, we can now substitute the value here, which is theta prime B is equal to negative 1562.547 and theta prime C is equal to negative 278.853. So to compute for the member end moment, so you just need to substitute the value of theta prime B by this value here, okay, and theta prime C by this value. So by computing the member end moment by using the computed values, we would get the value of MBA, which is equal to negative 423.7282. This is kilonewton meter. Now again, you use the value of EI here as 341,000. Now since we have negative value, that means the moment BA is 423.7282 and the rotation here is clockwise. This is clockwise because we came up negative answer. And for MBC, okay, now again you use the value of theta prime B here as negative 1562 and the value of theta prime C here as negative 278.853 and the value of EI here as 341,000. This would give us 423.7282. So as what you can see, we have the same value with MBA because again, this should be in equilibrium. So at point B, we should have the same left and right side moment. And this justifies the equation number 5 in which MBA plus MBC is equal to 0. Now for MCB, we have 803.8718 became a positive, therefore the rotation is in counterclockwise, the same as with MBC since we have positive answer. For MCD, we have negative 803.8718 kilonewton meter, therefore the rotation of our moment is in clockwise direction. So we have now the member end moments of MBA, MBC, MCB, and MCD. So we will now be using this value to compute for the reactions of each support. So we begin with member AB. So we will be computing for reaction at A and the left reaction of B. So in this case, we can sum up moment at B to compute for RA, and this equals to 0, counterclockwise positive. Now take note, we have the value of MBA here, which is clockwise based on our computation, okay, in which the value of MBA is 423.7283, that is in kilonewton meter. Okay, then we have here negative 423.7283 plus we have 32 times 5 times 2.5 minus RA times 5, okay? And this equals to 0. So we have RA here, which is equal to negative 4.746 kilonewton. This negative sign here implies that we have incorrect assumption. That means our RA here should be going downward. Okay, so RA is acting downward. To compute for RBL, we can just sum up forces vertical is equal to 0. Upward forces are positive. Then we have RA, that is negative RA plus RBL minus 32 times 5. And this equals to 0. So by using the value of RA, so we have RBL here equals to 164.746 kilonewton. So we have RBL which is equal to 164.746, RA which is equal to 4.746 kilonewton. And now for member BC, so we have here RB to the right of B, and we have here the reaction of the left side of C. Okay, so we have here moment BC. Now moment BC, from our previous computation, our moment BC is 423.782, which rotates counterclockwise. And moment CB is 803.8718, which rotates counterclockwise as well. So we have a counterclockwise MBC and a counterclockwise MCB. So we have the value of MBC 423.7283, and for MCB we have 803.7318. 803.8718 kilonewton meters. So we can compute RBR here first by summing up moment at C is equal to 0. Counterclockwise moment are positive, so we have 423.7283 plus 803.8718. These are all counterclockwise. Then minus, we have 5 RBR. Then plus 32 times 5 times 2.5. And this equals to 0. So we have RBR here, which is equal to, we have 325.52 kilonewton. So we have now the value of RB, which is equal to RBL plus RBR, which is equal to, we have 164.746 plus 325.52. The reaction at B is equal to 490.266 kilonewton. So this is the value of the reaction at B. And then we compute for the RCL. We can sum up forces vertical is equal to 0. Upward forces are positive. We have RBR plus RCL minus 32 times 5 is equal to 0. So we have RBR here, which is 325.52 plus RCL minus 32 times 5 is equal to 0. Then we have here RCL is equal to negative 165.52. So therefore, our RCL here is supposedly going or acting downward. So we have RCL, which is acting downward. And then for member CD, the last one, we have here the RCR and we have the RD. And of course, we have moment CD. Based from our previous computation, moment CD is 803.8718 kilonewton meter, which is rotating clockwise. So we have MCD here, which is in clockwise direction, and the value is 803.8718. So we can compute first here the RCR. So we have summation of moment at D is equal to 0. Counterclockwise moment are positive. So we have negative 803.8718. That is our MCD. Minus RCR times 5 plus 32 times 5 times 2.5, and this equals to 0. So we have our RCR here, which is equal to negative 80.774 kilonewton. That means we have incorrect assumption of RCR. So this is supposedly acting downward. So this one should be acting downward. So we can now compute the value of RC by summing up RCL and RCR. This would give us 165.52 plus 80.774. This would give us 246.294 kilonewton, and this is going or acting downward. Okay, now we have the RC. So we can now compute the value of RD by summing up forces vertical is equal to 0, upward force are positive. So we have negative RCR minus 32 times 5 plus RD equals to 0. So we have negative 80.774 minus 32 times 5 plus RD is equal to 0. So RD here is equal to 240.774 kilonewton, and this is going upward because we have positive answer. So our assumption of RD is correct. So we have now the reaction RD, this one. We have now the reaction RC, which is this one. Reaction B, which is this one. This is going upward. And we have the reaction A, which is this one. So our reactions are, for reaction A, we have a value of 4.746 kilonewton, which is acting downward. For reaction B, we have 490.226 kilonewton, which is acting upward. For reaction C, we have 246.294 kilonewton, which is acting downward. And lastly, we have RD, which is acting upward, and this is 240.774 kilonewton. So if you sum up all the reactions, you would have negative 4.746 plus 490.226 minus 246.294 plus 240.774. This is approximately equal to 480 kilonewton. Okay, we have error, a slight error because of the round off value, because of the decimal. So, and this should be equal to 32 times 15. And that means you have correct reactions. Okay? And that ends our second example on the slope deflection. So if you wish to watch the third part of the discussion, which I will discuss to you about how to apply slope deflection method to frame analysis. Now, thank you guys for watching this video. I hope that it helps you on your engineering journey. Thank you guys, and see you on my next video. But please don't forget to like this video, share it, and subscribe to my channel. Stay safe and God bless.